Hello, everybody. Hey, this is going to be a lecture on momentum. Now, when last week we talked about a bunch of stuff that we talked about last quarter, and that was all these basics like mass and inertia, movement, and whenever you have movement, you're talking about velocity and acceleration and displacement and time. And that's going to be a result of a force, which is just a push or a pull, which gives you Newton's law, like the first one, the law of inertia. An object in motion will keep its state of motion unless acted on by an outside force. And then we have energy, which is the ability to do work. Work is force times distance. And that can either change the kinetic energy, okay, or it can negatively change the potential energy. Essentially, we've got a conservation of energy. And the kinetic energy plus the potential energy is the mechanical energy. For our purposes, mechanical energy is going to be conserved. Now, what we are ignoring when we talk about mechanical energy, which is just kinetic and potential, is all of the internal energy, and that could be things like thermal energy and sound and that sort of thing. And so we are ignoring all that internal energy, and that makes things sort of easier to talk about. So even though in your head you know that there's this other stuff that like friction, etc., which is going to change the temperature of something, for mechanical energy works, we're ignoring all that. All right, so now kind of getting back to if we're talking about momentum. Now, in the beginning of last week, I had you make some observations about a Newton's cradle, and if we were to take an object, the one ball here, and we would lift it up, right? So we have increased, through our work, we're going to have a force times a distance, and we're going to increase the potential energy of this object, okay? And now we're going to let it go, and all of this potential energy, as the potential energy goes down, the kinetic energy is going to go up until it hits right here. And then this collision is going to then transfer all the way through, and we're going to see, as you saw in that video, that we're going to have a ball that kind of goes up. And according to conservation of mechanical energy, whatever height this is, this single ball is going to go up that same height. And then it would come down and do the reverse, and it would go on forever, according to mechanical energy. And obviously, we know that it doesn't go on forever, but that has to do with things moving out of the way, like air moving out of the way, which is going to increase the randomness of things. And that is that internal energy that we talked about a moment ago. Okay, but what conservation of energy does not tell us specifically, though, is that if we lift this first ball up a certain distance, height, and it comes down, what could happen is we could have two balls go up at half the height, and that would still be equal and explained by conservation of mechanical energy. But we never see that. If we have one ball come down, we're going to see one ball go up, two balls go up. When they come down, then we're going to have two balls going the other direction. So we need a different concept, and that concept is momentum. Okay, so momentum is pretty simple. Okay, momentum. We're going to use the letter P. We're going to use the letter P to signify momentum, and it is simply mass times velocity. Mass times velocity. Momentum is a vector quantity, as is velocity, and mass being a scalar quantity. So the key thing with momentum is that momentum is conserved. Okay. So when we have a conservation of momentum, this is of an isolated system. Okay, that means the momentum in the beginning is equal to the momentum afterwards. And if we take, for example, these two skaters here that I have illustrated here, that if we have two skaters, their initial velocity is 0. That means that the overall momentum of those two skaters before they push off is 0. So that means if they push off, their final momentum is going to be 0. So let's take a look at what that results in. So skater 1 and skater 2 are going to push off each other. Okay. Now, according to Newton's third law, for every action, there's an equal and opposite reaction. So when they push off each other, they're going to have the same force. The only difference is that one's going to be negative because it's going to push this way, and the other one's going to be positive, and it's going to push that way. So we're going to have mass 2 times acceleration and mass 1 times acceleration. And if their masses are different, and in this case they are, we're going to have 50 kilograms and 30 kilograms, their momentums are going to be different, and therefore their accelerations are going to be different. So even though we have the same force, that doesn't mean we end up with the same velocity afterwards. Okay, so now if we kind of go back to this side, we know our momentum final is equal to 0. And we're going to say that our velocity of our second skater here is going to be, let's say 6 meters per second. Okay, that means our M1 V1 final plus our M2 V2 final is going to equal to our initial momentum before, which was 0, because of conservation of momentum. So now we can put in numbers, and now we can say 50 times V1 final plus 30 times 6, that's going to equal to 0. And we can say that V final is going to equal to negative 180 divided by 50, okay? And that's going to be negative 3.6 meters per second. Okay, that is going to be V1 final. Okay, that is a very simple sort of equation, and this is going to be the same sort of thing that you're going to see in question of the day for 4-6. All right, so we can see that 50 times negative 3.6 is going to equal to 30 times positive 6. And again, that's going to add up to 0. That's going to add up to 0. So their momentums were conserved. Now, one question you might be bugging you is that we put energy into this system, right? Well, how much energy would that be? Okay, well, we know that work, the amount of force times distance that we do, is going to change the kinetic energy. So we're going to have 1/2 mv final squared plus 1/2 m2v final squared. And this, because the initial kinetic energy was 0, when we add up these kinetic energies, that's going to be how much energy that the force between these two skaters was. So we're going to have 1/2 times 50 times 3.6 squared. Now that is negative 3.6, but since it's squared, it's going to turn positive, plus 1/2 of 30 times 6 squared. Okay, and that's going to give us on the order of 850 joules. So 850 joules. Now, that's how much energy was exerted in the muscles of skaters 1 and 2 that they exerted. Okay. that would be the amount of mechanical energy that they converted. And a minute ago, when we were talking about that internal energy, there would probably within the bodies there would be some also some internal energy that was exerted that did not go into that 850, and it would have been exerted as heat energy. And so we can see that there's going to be a very minimum of 850 joules that the skaters would have done. And then it really would have been in excess of that because of that change in internal energy. All right. So essentially, this sort of question right here is what question of the day 4.6 is on. So if you're looking at that problem, you can kind of go back. You can kind of go back to this. All right. But we also have another concept when we talk about momentum, and that is impulse. Okay, so impulse is equal to the force times time. The force times time, and we very often call this I. So impulse I is equal to force times time. And this is going to be a vector there. And this is equal to the change. That's equal to the change in momentum. That is equal to the change in momentum. So when we want to change the momentum of something, if we give it a force times time, that is going to change the momentum. So, and remember, this would be mass times the change in velocity. And momentum and velocity are obviously going to have vectors. So when we talk about the two skaters, when they pushed off on each other, they had a force times time, okay, that they pushed off each other. And we know that there's a conservation of momentum is because according to Newton's third law, forces are equal and opposite. And the amount of time that those two forces would be acting on each other in the opposite direction would be the same amount of time. You cannot touch without being touched. So if you touch one finger for 1 second, you can't touch for less time with the other finger, right? So our impulse is going to equal to our change in momentum. Now, those two change in momentums went in opposite directions. So when you added them together for the system, they still added up to the beginning, which was 0. So the end is 0. Okay, so if we were just talking about one skater on the other, okay, then we could see that this force times time would be, for example, the one skater which had a mass of 30 times 6, right? So then that would have an impulse of 180 Newton seconds, okay? But that would also equal to meters per second, kilogram meters per second. So the units for momentum are kilogram meters per second. There's no fancy units for that, but that's also the same thing as a Newton second. As you may remember, a Newton is a kilogram meter per second squared, and then we multiply that by seconds, and one of those cancels out, so we get kilogram meters per second, kilogram meters per second. So those are the units. So this is pretty straightforward. I'm going to change this to a change in V. Now, if I were to, for example, be pushing something, let's say like a car or something, okay, and I'm going to have force times time, and I'm going to get this car to be going. Let's say it's a pretty small car, but let's say it is simply 100 kilograms, and our final velocity is going to be equal to 1 meter per second. Okay. Now it seems that our force times time was equal to 100 kilogram meters per second. Now, before we pushed, there was no momentum because the velocity was 0. So what was the counter momentum? Okay, so if I'm pushing on this, okay, the car is going this way. That means there had to have been something that was going that way. Okay, and in fact, it's the Earth. The Earth is going to be moving backwards like that. So if the change in momentum was 100 kilogram meters per second to the right, that means the Earth had to have a change in momentum that was equal to negative 100. And we're going to have and at first thought, you would essentially assume that the Earth did not move. Technically, it's going to move. Practically, it's not going to move. Because the mass of the Earth is equal to 6 times 10 to the 24th, that means the magnitude of the Earth going backwards would be on the order of 1 times 10 to the negative 24th, which is so imperceptibly small that we really wouldn't feel it. And so that's essentially what's happening. But we still have, even when we're talking about the Earth, we still have a conservation of momentum. All right. There's another thing about impulse, okay? And impulse is equal to the integral of all of the forces from t equals 0 to t is equal to t final. Now, you guys, I know that you guys worked on integrals last quarter, and this really is not going, we're not really going to be doing any calculus with this, but I wanted to sort of illustrate this with an example. And if we had, for example, a tennis racket and we were going to hit it, right? So as the ball came in a super slow motion, okay, right in the beginning, there would be a very, very small force, okay? And as we continued with this collision, the tennis ball would compress, as would the strings on the tennis racket would stretch. And so we would essentially load up all this elastic energy. The equation for that would be 1/2 kx squared. So there would be some sort of equivalent. And then when it would get to its apex, and then it would start to unload, right? And all those compressions would then turn around and uncompress and extend. And that would give us that sort of change in momentum. Now, if we were to look at a force versus time graph, okay, for that tennis ball being hit, we might see something like this, right? So right in the beginning where t is equal to 0, right when it came together, right, there's very tiny little bit of force, and as we move through time, that force would get greater and greater and greater until we had full compression, and then it would slowly unwind. And right as that tennis ball left the racket, there would be very little force on it, right? But if we want to take the area under this curve, that would equal to the impulse. Now, in order to make this integral, we would have to know what this equation was. And that, in a practical sort of sense, would be kind of difficult to look at. So what we're going to do in this class, and it's going to be super easy, is I am going to give you a graph like this, except instead of making it a curve like this, I might give you a triangle, right? and which we start out with zero force, we end up with zero force, and right here in the beginning, that would be our maximum force. Okay, but all we would have to do to calculate the impulse would be to calculate the area under that curve. But that curve is essentially just the area of a triangle. The area of a triangle. So easy, 1/2 base times height. Okay. It could also be something, let's say, you might see something like a trapezoid. Okay. So that that force would increase to a certain amount and then level off and then decrease here. So if you wanted to calculate the impulse using that graph, you just take the area of a trapezoid. It could even be, you guys, it could even be the original purple one, okay? But it would be in a grid, and all you would have to do is figure out how much one of those little squares would be, and then count all the squares that were underneath the curve. And if you had partial ones, you could just add up. If this was 2/3 of a square and that was 1/3 of a square, then you could put them together and make it into a whole one. And so you can estimate actually by counting the number of boxes and putting in partial boxes together, and you could estimate what that impulse would be. And if you know impulse, then if you know something about the mass and one of the velocities, you could figure out what those other velocities are. So again, impulse, that's going to be a pretty simple type question, because we're not really going to get into those integrals. It's just going to be that area. Okay. So next, our next topic here, and we might need a little more room here, would be there's three types of collisions. Okay. So as we come in here, if you had a tennis ball hit a tennis racket hit a tennis ball, that's obviously a collision. So there's three types. There's going to be inelastic and there's going to be elastic. Okay. Now that's only two, but if we look here, we're going to have either perfectly inelastic or perfectly elastic. Now, from a kindergartner's point of view, an inelastic collision is when two things hit each other and they stick together. And an elastic collision would be where they hit and bounce, Okay. Now, if we have, let's say, a tennis ball, okay, and I drop a tennis ball, it's going to bounce. So clearly, we would call that an elastic collision because it hits and bounces. But that would not be perfectly elastic, because if it was perfectly elastic, from whatever height we dropped, it would hit and go back to the same height, and that would be perfectly elastic. If we have something like this clay ball and we drop, okay, it is going to hit and stick. It's going to hit and stick. And that would be a perfectly inelastic collision. Now, obviously, when we drop this down, it doesn't quite stop there. It's going to roll around, and that's why it's not perfectly inelastic. So anytime we see an object that's going to hit and bounce, we'd call that an elastic collision, but we might not call it perfectly elastic, which is going to give us our third type, which we would call partially elastic, okay? Or just elastic, just knowing that it's not necessarily perfectly elastic. You could obviously, by the same vein, call it partially inelastic. All right, so those are our three types. Now, it is important to realize that there are certain conditions on this that will help us when we are making calculations. And I'm going to switch this over here a little bit. Okay, so when it comes to kinetic energy, okay, in an elastic collision, the kinetic energy would be conserved, and that's why if it was perfectly elastic, when it bounced, it would go back to the same height. And in an inelastic collision, kinetic energy was not conserved. And if we were to just think about this clay ball, if it were to hit and then suddenly stop, all the kinetic energy is lost, and therefore it is not conserved. But in both cases, in actually all three cases, our momentum is conserved, both in elastic, inelastic, and partially elastic. Momentum is always conserved. Momentum is always conserved. Whew. All right, and that is going to help us. All right, so now when we have these types of collisions, and for the most part, we're going to talk about either perfectly elastic or perfectly inelastic. And when there's something in between, we still know that there is going to be a conservation of momentum, and we might need other information. All right, so I'm going to write the equations for the different types of collisions, and we'll kind of see how easy that is. All right, so the easiest one is inelastic. So for inelastic, we're going to have M1 V1 initial plus M2 V2 initial. That would be our initial momentum, and that would be M1 V1 final plus M2 V2 final. But if they hit and stick, then the masses are now together, okay? So we can call it just M1 plus M2. And because they hit and stick, their velocities of each other are going to be the same. So we're going to have V final, okay? So this is our equation for a perfectly inelastic collision. And we can see that if we know the initial mass and velocities before, then we can calculate what the final velocity is. And you're going to see that in a question of the day later this week. All right, so now brings us to the elastic collisions. And we are going to end up essentially having the same M1 V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. Now the problem here is if we knew all the information here, we have two unknowns. We have two unknowns here where in the last one we only had one unknown, and we need a second equation. And that second equation is 1/2 M1 V1 initial squared plus 1/2 M2 V2 initial squared is equal to 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. And we can see that this right here, because we've got a first order velocity here and a second order velocity here with kinetic energy, that it looks pretty nasty, okay? And sorry about that. So what happens here is when we combine these two equations, we're going to end up with the following equations. And you guys can combine it if you like to work around sort of more complicated equations and integrate them. It's kind of fun to do, okay? But barring that, here is the result of how to calculate the final velocities of two balls in a perfectly elastic collision. So we're going to have V1 final is going to equal to M1 minus M2 divided by M1 plus M2 times V1 initial, okay, plus 2M2 divided by M1 plus M2 times V2 initial. and that will equal to M1 final. Now, if your second ball is initially at rest, then this whole goes away, and it becomes essentially a simpler equation, okay? Now, V2 final is going to equal to 2M1 over M1 plus M2 times V1 initial plus M2 minus M1 over M1 plus M2 times V2 initial. And these right here are the equations for calculating the final velocity of a perfectly elastic collision. And if we have, if the two masses are the same, when they are coming together, let's say we have these two masses, they come together and they hit and stick, okay, then we don't really need much math to calculate this. We're going to calculate the average of the first two velocities, okay, and that's going to give us our final velocity. Again, that's for an inelastic collision. So if this one is coming in at 4 and this one starts out at 0, we're going to say 0 plus 4 divided by 2. Our final velocity of the two objects are going to be 2. So they're going to move across this way with a final velocity of 2. If we've got positive 4 and negative 4 and they're going to hit and squish, okay, inelastic collision, then we're going to take the average of positive 4 and negative 4, which would be 0. So they're going to hit. And remember, all of that kinetic energy is going to go away in that case. And that is why when you have a collision like that, that these objects, like two cars, would deform and they're going to mush together. Okay. All right. So now, if you take the velocities for a perfectly elastic collision, okay, this is actually easier. And again, only if the two masses are the same. Okay, so if this was 0 and this one came in at 4, okay, and they hit, okay, what's going to happen is they're just going to exchange. They're just going to exchange their velocity. So this one was 0 and this one was 4. This one would end up being 4 or 0, and this one would end up going 4. Okay, so they're just going to exchange. If they were going 4 and 4 and they came together, they would bounce off each other and they would exchange their velocities. So this one would be negative 4 and this one would be positive 4 once they bounced off. Okay, so again, that would work with other things. So where it makes it a little more complicated is if their masses were different. But otherwise, it's pretty easy. All right, and that is today's lecture on momentum and collisions. All right, so we will talk to you guys next time.